Hello and welcome back. Today on the bench we've got a load of very high voltage capacitors. These capacitors came from me friend Ian out of his scope. I can't remember what the bloody make is just at the moment. Anyway, these capacitors form part of the voltage doubler circuit that provides the EHT for the cathode ray tube. As you can see, they're Marcon brand oil caps, so paper in oil, 0.5 microfarads, 1500 volts DC working. As I say, non-polarized. So there's two ways you can test caps. Obviously test them for capacitance, but the thing that we're really interested today is the leakage. In a very high voltage, low current circuit like that these are part of, leakage really affects them. So the symptom was of the fault that he'd put the scope on, got a trace, and then after a while the trace would disappear. For that particular brand of oscilloscope, which I have again forgotten, this is a known fault, and it's pretty much of a known fault in all vintage analog oscilloscopes. So as I said, we're interested in the leakage. All a capacitor is some sort of conductor material like metal. In a lot of cases in capacitor it's a metal foil wound round and round and round, separated by some sort of insulator. The insulator could be air, it could be paper soaked in oil, as in this case. It could be paper soaked in wax, or some sort of wax paper, or some man-made plastic. Doesn't really matter. What happens over time is that the insulation material or the chemicals in it start to break down, and then we start to get leakage. If you look at a cap, it's not just a capacitor, an ideal capacitor. It's got a few sort of different elements, as it were. We've got the capacitor itself, and we've got a sort of equivalent series resistance. That's because we've got to push some sort of current through the insulation material, and typically that's in the region of either tens or hundreds or even thousands of mega ohms, but it can be less in a lot of electrolytics. In this particular application the ESR isn't really important. In some circuits and applications it is more so, like in switch mode power supplies. There's also an equivalent series inductance, because if we've got lots of wound elements, like be it metallic or whatever, then there will be some inductance. That tends to be less important in our calculation, so we'll ignore that for now. So I'm going to test these capacitors with a few different circuits. This is the circuit that I've got here. It's basically a voltage doubler which is plugged into my variac and isolation transformer, a 220k limiting resistor, another resistor, a neon lamp, a 22N cap, and this is our capacitor under test. This circuit is more of use when we're testing electrolytics. For now I'm mainly using the voltage doubler, and then what I shall do, I shall also connect my ammeter here, and that gives us a good indication of whether the cap is leaky. If you don't know the particular specifications for your capacitor, you can use this formula here, which is 0.01 times by the capacitance, 0.01 times by the capacitance times by the voltage. And so for these capacitors in question, if they're working correctly, then we should have something like 7.5 microamps or less. Let's bung them on the tester and let's have a look at what they actually are. Right, I've got this doing set up for 500 volts. I've got the meter reading microamps. I'll hit the switch if I can find it. So we've got a bit of a surge and an inrush, but already you can see we've got a too high a reading. That's reading 61 microamps and it's staying steady at that. I would expect that if we watched it over a period of 8 minutes to start increasing as the insulation starts to break down more or the capacitor starts to warm up. So let's click that one off and then I'm going to discharge that. I've got my cap discharger which has got a 100 ohm resistor on there, but if we use that straight then it will blow the fuse in the ammeter. So I've just got a what's that, 200k on there just to limit the current through the meter. Just bring that down to something more sensible, because this capacitor, though it's faulty, it can still bite. There we go. Just use this voltmeter just to check, because we do have to be careful. You see that's just holding 6 volts. That's harmless, so we know that one's no good. Fuck that one off. On to number 2. In the where do you call it, in the oscilloscope, 2 of these, well there's 4 of these, but there's 2 sets of 2 capacitors connected in series to give a working voltage of 1500, no hold on, to give a working voltage of 3 kV, but obviously then the capacitance is halved, so that would be 0.025 or 25 nanofarads. Right, let's see how this one does. And that one's a little bit higher, 75 microamps, 10 times higher leakage current than we need. Number 3. This one's a little bit better, but it's still too high. And remember, we're only testing at 1/3 of the working voltage. What we'll do in a minute, we'll use this beastie that you can see at the back to test it at full working voltage, or approximate full working voltage. Right, so that one's no good. Right, and this is the last one. I think we've probably missed one, but you get the general idea. Right, this one's well high, about 100 microamps, no good. So just to have a sanity check, what we'll do, we'll test a new one, and we'll also test the ones that I'm going to give him as a replacement. Right, here we go. These are, I'm going to give him these ones to replace those 5 capacitors over there. These are W, new old stock, type 490, and they are 0.03 plus or minus 20% microfarad 3 kV capacitors, made in 1976. These are, oh no, you can't really see some of these. I've seen some of these where they've got like some sort of oil, but I presume they are paper in oil. But as you can see, the construction is a lot better. They seem to be some sort of soldered metal case. I'm not quite sure what that is made of. Right, let's have a look at see how these test. And as you can see straight away, there is a really big difference. These aren't really reading at all. So that just goes to prove that the other ones were no good. And to give ourselves total confidence, we'll test a brand new capacitor. So this one here is a NKP polypropylene or poly something or other, poly put the kettle on, 470 nanofarad, 850 volts. Let's have a look at this one. As you can see what we've got there, 0.7 microamps. So that just goes to show you the capacitors that we tested are well shot. So after testing this one, to give us a bit of a sanity check, I'll get the big ionisation tester out and we'll test the capacitors at pretty much full working voltage. Okay, well we've got the big air mech ionisation tester connected to a capacitor now, and we'll test this one at 1000 volts and see what we get. As some of you may have seen me use this in the past to test transformers and that sort of thing. What this is doing is applying a high voltage 1000 volts across the capacitor. It's listening for any insulation breakdown, whilst at the same time measuring the insulation in mega ohms. So this is 1000 volts. As you can see, that's not reading full potential. If we flick it on to the 100 microamps range, that will give us a better reading. A good capacitor should be all the way over here. So that is reading about 1.1 on the 100 microohms. It's a bit hard to say this is. On the 100 microohms range at 1000 volts, we times that by 10. So 10, so about 10 meg, 10-11 meg. So what we'll do now, we'll put one of the replacement caps on there and see what sort of reading we get there to give us an indication of what a good capacitor should test. Can't really show the capacitor in the same frame as the meter. Let me try and zoom you in a bit. As mentioned, the meter should stay over here. As you can hear, right, that's recording a little bit of insulation, sort of weirdness going off, but nothing heavy. If it was really bad, you'd hear click 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 really loudly. So as you can see, we've got a reading of infinity. Turn that down. Click it on to 10. Let's click it on to 1 microamp. The lower the current, the higher the sensitivity of the reading. Now here we go. So that's reading between 4 and 5. If we're on the 1 micro amp range, we've got to times that by 1000. Oh, and that's just gone to 10 now, which is even better. So that's, what is it, 10 times 1000, 10,000 meg, which is, yeah, a very good reading. Let's see if we can test. Got to be careful there because they're full of high voltage. Let's test one of those duff capacitors on that same setting and see what we get. Right, well that's just telling me that, yeah, it won't even read. Remember, we're still not testing this at its working voltage. No, won't read. So let's, for a laugh, click this onto 10,000 volts, put it on the volts reading and see what it says. Testing at its full working voltage. Now this is reading voltage. This is reading voltage at the top, so we've got about 1000 volts. and as you can see we can't really get a full reading on there. It won't even go to 10,000 volts because the leakage is such that it's leaking faster than the test gear can supply it with voltage. And to give a comparison, we will test one of these big jobbies. As you can see, this is a Gert Big Type 06, 1250 picofarad plus or minus 20%, 10 kilovolts working voltage. And these are, it doesn't really give a make. These were made in 1975. I'm connecting that up now, and so we can whack this all the way across. So as you can see, there's a totally different result. The meter deflects all the way over to the right. Anyway, I'll bung them on eBay. Somebody might be able to make use of them. So I hope you found that useful. A little bit of a dive into capacitor leakage. As mentioned, it's important when we're dealing with high voltage, low current circuitry, things like amplifiers, transmitters, volt transmitters and that ilk, because any leakage will just, it will knacker the circuit up and it won't work. Thank you all for watching. Ta-ra for now.